This video lesson covers covalent bonding and molecular geometries. As we think back to what we learned about naming covalent compounds, these were the ones that we utilized prefixes to provide a name to the combination of elements. So when we went through and looked at some practice problems when we did this, for example, if you have sulfur with 3 oxygens, it became sulfur trioxide. If you have nitrogen with 3 oxygens, N2O3, it was named dinitrogen trioxide. So what we have to understand now is how the periodic table properties allow these types of combinations of elements to form. So the first part of the video lesson, entitled Covalent Bonding, will discuss this. With covalent bonding, you will find that electrons are shared between 2 or more atoms. And the way that they are shared depends upon the electronegativity of the 2 or more elements that are involved. On the left-hand side, you will see that we have chlorines, 2 chlorines bonded together, creating what's called a nonpolar covalent bond. It is nonpolar because there's 2 atoms that are equal. There's 2 chlorines, they're the same atom. Versus on the right-hand side, illustration B shows us the combination between hydrogen and chlorine. This is considered to be polar covalent because the electronegativity between the hydrogen and the chlorine are different. This also leads us to something called partial charges, also known as dipoles, covered in a unit denoted dipoles. As we again look at the effects of electronegativity and we look at the characteristics of nonpolar versus polar, the combination of elements makes the difference here. Fonkel bricks, our trend for electronegativity, will help us with this. Something that is considered to be nonpolar will share an electron equally. Why? Because there are no differences in electronegativity. This results in a symmetrical shape. In other words, you will have a homonuclear diatomic type molecule. So this will occur whenever we are looking at scenarios such as 2 chlorines bonded together. Okay, so Cl2 would be homonuclear diatomic. We could look at 2 nitrogens bonded together, okay, which would be triple bonded, as we will see, N2. And the opposite of that would be polar covalent, unequal sharing of electrons. Why? Because you have a difference in electronegativity. This is going to give us a non-symmetrical shape, and it results in heteronuclear diatomic molecules. So for example, you could have the combination between chlorine and, for example, a carbon. Now, a carbon is also going to have other things bonded to it, but the electronegativity between the chlorine and the carbon would be different because it's 2 different atoms. A smaller version would be hydrogen combined with iodine, 2 different atoms. And we can look at the electronegativity differences. As you saw on the previous slide, they do swell out, giving you a non-symmetrical shape. Versus whenever you have 2 of the same atom combined, they're going to look symmetrical because the electronegativity differences between the 2 are the same. So as we look at the periodic table and we focus in on the upper right-hand quadrant, it may hopefully bring to mind what you learned with the trend of electronegativity, that as we go up and over towards the right-hand side of the periodic table, where we see fluorine, we have the most electronegative elements, followed by oxygen, nitrogen, chlorine, and so on. With the formation of a covalent bond, you will notice that we are focused in on 2 very important things happening. Number 1, energy, and number 2, increasing or decreasing internuclear distance. So for example, and both illustrations show us this, but I'm going to use the larger of the two. If you look at the hydrogen atoms that are by themselves, these two, you will notice that based on their distance, they are too far apart to bond. But as the distance decreases, relative to that, the amount of energy also decreases. So as we go along the graph and the distance between the two atoms becomes close enough together so that you can create a nice bond between the two hydrogens. So we have a minimum distance, and at the same time, the minimum distance also reflects a minimum amount of energy to allow for very, very good bond formation. As you continue along, you will notice that if the two atoms become too close together, then the bond formation is cramped and it's not considered a stable bond. So we're looking for that minimum distance and minimum energy. With covalent bonds, you will find that we focus also on single, double, and triple bonds, and they will reflect a certain number of electrons, referred to as a certain number of pairs. And as we look at the length versus the amount of bonds, you will notice that a single bond is considered the longest. A double bond is in between because there are two of them, and a triple bond is the shortest because there are three of them. This is also going to be the one that is the strongest, made up of the most number of electrons, whereas a single bond is the least number of electrons. And it also reflects the number of pairs. So when we talk about electron pairs, you will notice that with a bond represented by a line, in order for a bond to form, you have to have electrons. So if we use dots to represent our electrons, we have to have two of them to form. Our covalent bonding regions are also going to be the areas that reflect what we did in terms of naming. So these were the ones that required the prefixes to name. Notice that we are covering just about all of the top portion of Roman numerals 1 through 8a. We're also picking up the noble gas xenon that will be involved in this as well. And as we start to build our structures, we're going to notice that we have a certain number of rules. So as you look at this particular slide, I'd like you to keep in mind that the general rules for building covalent compounds are as follows. You're going to place the least electronegative element in the center. We're going to look for symmetry as best as possible. It's not always going to be feasible, but try to make it symmetrical. The element hydrogen always forms a single bond and it's never in the center. So one of the points that I want to leave you with as I get towards the end of this first video lesson is that if you have the element hydrogen, hydrogen happens to be located in Roman numeral 1a, which means that it has one valence electron. So it has one little electron on it. That means that it can only form a single bond. So as you extend a bond from the hydrogen, it's going to then attach to something else. So this is the visual that I want you to look at as you always think about hydrogen. Halogens, rule number 4, are usually single bonded. And again, I use the word usually because sometimes there will be exceptions to this. But let's say, for example, we take the element chlorine. Chlorine happens to be located in Roman numeral 7a. So we know that chlorine is going to have 7 valence electrons. So we'll use 7 dots to represent our valence electrons. Well, similar to what you just saw with hydrogen, this means that they typically only form a single bond. Why? Because there is only one valence electron that is free to make the bond. This concludes this initial portion of the bonding lesson, and you'll be ready to continue on with the second lesson that will show you how to construct these molecules.